Okay, good morning. So it's 1 minute to 9, so it's time for me to give an introduction to this session of pets on censorship and fingerprinting. Well done for being here after the banquet. I'm sure that it was hard, but you will be well rewarded with one of the most interesting sections of this symposium. I have a couple of announcements. First of all, for the sake of the poor people who are listening to this online, we need to speak all the questions into this microphone. So when you raise your hand and have to ask a question, please wait for the microphone, otherwise no one has any idea what's going on. The second thing is, if you feel like turning pets into an episode from Black Mirror, feel free to rate people online for their talks, okay, or give them comments or whatever, badges or, you know, whatever. So don't forget to do that if you're like this, okay? And so that we don't actually delay the proceedings anymore, it is my great pleasure to invite Diogo Barradas to talk about DeltaShaper on censorship circumvention.
Thank you for the introduction. Can you all hear me? I guess. Good morning, everyone. So I will be presenting DeltaShaper, a censorship-resistant system which offers the covert TCP IP channel over Skype video calls. This is joint work with Nuno Santos and Luís Rodrigues at Inesquide in Lisbon. State-level censors actually monitor and control internet access and may prevent their citizens from accessing or publishing information online. In a typical setting, Alice, here depicted on the left, is inside the censored region and tries to access some foreign service, such as the New York Times. Usually, censors can deem these access as prohibited, and they actually block it by performing techniques such as DNS hijacking. However, censors do not block all the channels across their borders, and one of the services that is usually available is Skype, which allows Alice to talk to Bob. Since these services are allowed across the censor's borders, they become a prime target for the development and deployment of covert channels, which may allow Alice to use Bob as an intermediary to access her service like the New York Times. So lately, censors have been keen at trying to detect and thwart the functioning of these covert channels, either by applying traffic analysis techniques to understand patterns on the traffic that deviate from the common behavior of the protocol, the carrier protocol, and also to apply network perturbations in order to thwart the correct functioning of the covert protocol. So with this work, DeltaShaper, our goal is to establish a TCP/IP covert channel over a Skype video call in a way that we can maintain an observability, that is, the channel can resist against traffic analysis from the sensor, and also resist against network perturbations that the sensor responds. Actually, DeltaShaper is not the first system to explore the idea of multimedia protocol tunneling, where data is encoded in a channel of a multimedia protocol streaming. In fact, we have focused on two main properties of these systems, which are security. That is the ability of the system to resist against active and passive attacks launched by the sensor, and also to provide coverage. That is the range of applications and use cases that a user can use our coverage channel. So some of the characteristics of this kind of coverage are the ability to transmit arbitrary data and to perform interactive communication, allowing Alice not only to consume or to publish content, but both. One of the first systems to explore this idea of multimedia protocol tunneling was Freewave, where data was encapsulated in the audio channel of a Skype call. Albeit this system is provided for arbitrary data transmission and interactive communication, it failed to provide active and passive attack resistance. At the other end of the spectrum, we have CovertCast, which encodes data into the video layer of live streams such as YouTube. And although this system allows us to provide active and passive attack resistance to a sensor and the transmission of arbitrary content, it does not provide for interactive communication. So with DeltaShaper, we are trying to match all these three characteristics and offer a channel which also provides interactive communication. In our threat model, we assume that the packets carrying the multimedia data are ciphered, and Skype already gives us these. For the sensor capabilities, we assume the sensor to be able to perform deep packet inspection, to be able to observe, store, and analyze all the traffic flows crossing the sensor's borders, and also to apply artificial constraints on the network. However, the sensor is limited, and it is unable to decipher the content of these Skype packets, and it is not in collusion with the video conferencing provider. So this means that the sensor is unable to watch live the stream which is being communicated between Alice and Bob. The sensor also attempts to minimize collateral damage, so it will only block a given Skype stream if it knows, if it has some evidence that that stream is being used to convey a covert channel. So how can we encode data into the video layer of such system? A naive approach will be to replace all the chat video frame, which in Skype consists of a 640 by 480 pixel, with all data. So if we encode data naively, for instance, replacing all the RGB channels of each pixel with data, we could encode about 24 bits per pixel, what will give us a throughput of about 920 kilobytes per frame. However, this naive encoding has two major drawbacks. The first drawback is the issue of data loss. Since the color of a single pixel cannot be faithfully represented due to the downsampling and the quantization processes of video codecs, we cannot really extract the information encoded in a single pixel. The second major issue is about the generation of abnormal traffic patterns, since the lack of spatial and interframe redundancy between frames, that is, in these kind of frames which encode a lot of data, there is not a single area of the frame which is equal or with many pixels of the same color. And there is not also a queue from previous frames to next frames, so how to shift the scene. So we try to answer three main questions and challenges. The first one is to be able to perform the distinguishing between regular and irregular Skype streams. What I mean by regular Skype streams is just a regular video call that you can pose with someone. And the irregular Skype stream would be some channel or some data encoding that the sensor could identify. So just by looking at the packet length frequency distribution, we can see that if we encode different frames through Skype, the traffic signature generated is quite different. For the first example, where we encode data naively, we can see that the codec is able to perform a poor compression, and then there's a lot of large packets being transmitted through Skype. In an average compression, we show a video of someone performing a Skype call, where there exists both spatial redundancy, for instance, in the background of the picture, and also interframe redundancy, where following frames are very similar to the previous one. In the last case, we have an example where frames do not change at all, and then the codec can perform its highest level of compression, and where frames do not change. So this brings the challenge. So how much throughput can we achieve while preserving the observability of our channel? Even if we ignore the issue of data loss, the first picture, which shows us the naive encoding, will yield us a high throughput, but a poor on observability. In the contrary, if we just embed a small payload area, let's say we encode 4 bits in a black and white matrix on just the top of the regular call, in fact, this video pattern will be very similar to a regular Skype call, because the codec will reflect the video behind this payload. And so we can achieve good on observability, but this channel will have a low throughput. Also, even if we reach an encoding which provides good on observability in some ideal network conditions, we have seen that sensors can affect network conditions, for instance, by dropping bandwidth, and this can make a pattern emerge on the channel, which makes it observable. So we need to adapt to these network conditions. So the major contributions of our paper are a prototype of this system, DeltaShaper. We propose a method for distinguishing regular from irregular Skype streams, and here we will use the packet frequency distribution combined with a metric which is called the Earth Movers Distance, we'll talk about in a minute. We propose a method for maximizing the throughput available on our covered channel, but in a way that we can always maintain an observability. And we also introduce the issue of adaptation to network conditions in order to dynamically calibrate these parameters. To characterize Skype streams, we define two major metrics. The first one is a characteristic function, which enables us to create a signature of regular Skype traffic. So for this, we have used the frequency distribution of packet lengths. We have explored other metrics on our paper, but we found this one to work best. For the similarity function, to quantify the differences between different Skype streams, we have used the Earth Movers Distance, which intuitively gives us the cost of transforming one signature into the other. Armed with these metrics, we can really see that the Earth Movers Distance is able to quantify the differences between Skype streams. And here on the left, we have a regular Skype call when compared to different videos transmitted through Skype. In the first example, we can see that the comparison between a regular video and a naive encoding will yield the Earth Movers Distance of about 50%. The same happens with the encoding, where we just stream one blank background on the Skype stream. And you can see that between regular Skype streams of people talking about each other, we can achieve an Earth Movers Distance of about 5%. And this is quite stable for different videos. So a sensor armed with this information can establish a delta threshold, let's say 6%, above which it will block all the calls which do not seem to be regular. So our real challenge is to create a channel, a cover channel, which can be below this threshold. And we have seen that in our strawman approach, if we just encode a little area of payload on the frame, we are able to maintain under this threshold, and thus the sensor will identify our channel as a regular call. So looking at this picture, we can think to that this kind of encoding area on the frame is a parameter, but it is not the only parameter. In fact, we have tried different parameters on our exploring of encoding configurations, and we have come to the conclusion that to create a payload frame, which is embedded in a carrier frame, which is just a picture from a regular call, we are able to configure this with the payload frame area on top of the carrier frame, the cell size, which is a block of pixels which encode a given color and hence a given number of bits, and also to shift the payload frame rate, that is the frame rate at which this payload area changes on top of the regular video. Changing the cell size and bits encoded per each cell allows us to accommodate for data loss due to the compression, and for choosing the ideal parameters for encoding our data on our channel, what we do is to take a greedy approach, trying to start by encoding a large payload frame, a large payload area, and with minor cell sizes so that we could encode more information. And then we try several parameters until we can achieve one that allows us to both resist data loss and also to keep an observability. And the idea is to maximize throughput. To adapt to network conditions periodically, we try to calibrate these encoding parameters, and what this yields is just the idea to maintain the unobservability of the channel, for instance, by using a smaller area of payload and also shifting the number of bits we are encoding. In practice, we do this kind of adaptation periodically. So periodically, we just stream the carrier video without embedding any payload to get a signature of that carrier video on that particular network conditions. Then we compare this signature with the baseline of different signatures captured of regular videos captured in different network conditions, and we try to assess which one is closest. We take that as the representative of the current network conditions, and then we choose the parameters from a pre-recorded table. For implementing DeltaShaper, we have tried to overcome three main challenges. Only takes to network interaction, because we wanted to use TCP/IP applications without the need to change them, either the client or server applications. We have tried to perform video processing in order to combine these carrier and payload frames that we are generating. And also, we'd like to use the video conferencing software as a black box, and so we do not want to change the video conferencing software. This figure shows us an overview of the DeltaShaper client module, and we can see that the client application is run inside the Linux network namespace, and the packets generated by this application are then grabbed by a kernel module that we have developed, and the IP packets are forwarded to the payload encoder of DeltaShaper. These encoded packets, which in fact will give us payload frames, will be then combined with carrier frames through a stream blender called SnowMix. The resulting video will then be delivered to a virtual camera device from which Skype can read seamlessly, so we do not need to change the Skype software. On the server side, we have a photo thread which keep taking screenshots at the Skype video display frame buffer, and the resulting frames that are captured are decoded, and the resulting IP packets are then delivered seamlessly to the server application. To evaluate our system, we try to answer three main questions. The first is, can we distinguish Skype streams in practice? Can we balance the throughput and observability of our channel? And finally, we evaluate the performance of DeltaShaper. To distinguish Skype streams, we try to put ourselves on the shoes of the sensor. And since these streams can be different, what we did was to combine the comparison of regular Skype calls and YouTube videos depicted on the right when compared to a regular Skype call. So we can see that regular calls, when compared between themselves, exhibit a very similar pattern, and that does not happen to YouTube videos. So if we assume a sensor to be performing this kind of threshold to separate between streams, it could yield a delta I threshold. So to build a DeltaShaper channel on these conditions, we must remain under this delta. To balance the throughput and unobservability of the channel, we run our greedy encoding exploration, and we have reached an encoding which gives us 320 by 240 pixels of area of the payload frame, with a cell size of 8 per 8 pixels, encoding 6 bits per frame, per cell, which allows us to resist data loss and also shifting the payload frame rate 1 frame per second. So we need to assess how the performance of this channel. And with this configuration, we have achieved a raw throughput of about 7.2 kilobits per second and a round trip time of nearly 3 seconds. This performance is able to use high latency and low throughput applications, so that we have enacted 7 use cases, both comprising of non-interactive and interactive sessions. And we can see, for instance, that it is possible to use DeltaShaper to download a file through wget, or for instance, to establish an interactive session to the server using SSH, and then sending an email through an SMTP server located on the server endpoint. Despite the overheads of our channel, we are able to cover a large space of use cases. For concluding this talk, I'd like you to keep in mind that we have developed a prototype of DeltaShaper. We have proposed a method for maximizing the throughput and maintaining the observability of our DeltaShaper channel. And we have introduced the issue of adaptation in multimedia protocol tunneling, which we have found to provide improved observability and may also be applied to similar systems which work with multimedia protocol tunneling. Thanks.
Speaker first. Yeah. Cool. And we have a few minutes for